Today, I wanted to describe for you the components of a Shield system. Shield is a system that is designed to automate the collection of data, the computation of metrics and waveforms in production and laboratory settings. The heart of the Shield system is the Nvh controller. The Nvh controller is a device built on a National Instruments PXI chassis that allows you to collect data in one of several different types of DSA cards designed for microphones, accelerometers, other dynamic data, counters for speed, CAN bus inputs if you happen to be working with that type of data, and also MIO cards if general purpose voltages are part of the support data for your data set. There's an embedded controller that's running a LabVIEW real-time operating system, and it has on it what we call an Nvh Controller Driver, which is an application that we've created for it that gives it the personality to become an Nvh controller. So the Nvh controller is collecting data from some kind of test machine in the form of sensors and speeds and bus data. This test machine might be a production end-of-line test machine, one of several that are testing some kind of axle or transmission or engine or something of that nature. And it could just be a laboratory development test cell engaged in audit testing, something where standardized data sets and repetition are the objective. So the Nvh controller does not know how to sequence itself. It requires some kind of a machine control device, either a PC application or a PLC. Typically a PLC will be what a production machine will have. And that machine control device will tell the Nvh controller when to start taking data, when to stop taking data, and what processing definition or configuration file to run on the data to produce results. The configuration file is created by Shield. Shield is the PC application and represents the real brain of the overall Shield system. So in Shield, you will take a data file, a sample data file. You will then use it to design NVH metrics and their associated waveforms that allow you to determine pass-fail. So the configuration file that you're going to create both defines how the hardware will be configured, what channels will be turned on, what sample rates will be run, and it includes the processing definition that tells how to take time histories and turn them into waveforms like order cuts and power spectrum and the like. The configuration file meets the data file, produces the results file. And the results file will have metrics and names, the limits that metrics are tested against for pass-fail, the pass-fail status, metadata that might come from the test stand in the form of what test stand am I running from, who's the operator that logged in today, what date, what time, that type of information, and of course waveforms, which spectrum and order cuts and the like. So we want to be able to produce a results file from Shield. We want to be able to consume data files with Shield at the PC level. The Nvh controller is going to create the data file, and we are going to end up potentially creating tens of thousands or even hundreds of thousands of data files in a year. So all that data has to go somewhere. It does reside on the Nvh controller for a period of time. There is a disk drive built in, and that data will stay resident on the Nvh controller for a few hours, a few days, a few weeks, maybe even a few months. But eventually, it has to migrate into the database, and that's Trove, our data collaboration server. Trove as a PC application runs on a server-grade PC, typically somewhere in the plant or somewhere in the lab, and it has built-in scanner. This scanner runs a route of IP addresses representing each Nvh controller in its domain, typically more than one. That whenever a new data file is created, the scanner picks it up, moves the data file, the results file, and the configuration file along this path into the database. The database then can be used to create queries on the metrics. Those queries can then be sent to the report definition engine. The report definition engine can be used to create reports that would be typical SBC charting, things like X-bar charts, R-bar charts, histograms, and tables. That then goes to the job scheduler, and the job scheduler decides when to run the report, which might be, say, once a day, once an hour, whatever suits the task. The query engine can also be used to identify just a list of file names. A list of file names is what the batch processor needs. Now the batch processor in Trove is exactly the same computation engine that resides in the Nvh controller and also in Shield. Shield can make a results file out of a data file. The Nvh controller makes results files out of data recordings, and the batch processor makes results files out of data files that it addresses from the database. The processing definition file that the batch processor needs is exactly the same config file that is made by Shield. So with the batch processor, you can take pre-existing data files, a brand new processing definition, and do what-if experiments with metrics of your own design. This is very powerful. It allows you to do what-if studies on historical data sets for product development evaluation, and also maybe to go back and design a new metric to detect some kind of quality, or the effect of some kind of quality spill that resulted in bad product leaving the plant. You can go back, say, grab the last 10,000 data files, run a batch sub on them with a brand new metric definition, and see what production might have looked like for those 10,000 files had you had your metric in place, and from that statistic maybe predict what the future pass-fail rate will be when you take that new metric live over in the Nvh controller. So with these various elements, we have a tool which is very powerful, very flexible, but its main purpose is standardized data sets. We want to have a set of configuration files that run on the Nvh controller that represent a sort of a standard formulation. We want the ability to change that formulation at will, but basically once it's locked down, that's the formulation that people are expected to use. In a production floor, it makes perfect sense. You might have a 3 or 4 step test representing slow speed ramp, high speed, and another low speed after the part's warmed up, and that will run for years at a time. In a laboratory setting, maybe the goal is to have a very consistent self-documenting audit test that an operator can run 8 or 10 times a day, that you can count on not changing for months and months, even years at a time. So it's a very powerful system for the automation of the collection and processing of Nvh data in the form of spectro, order cuts, impulse indicators, and many, many other kinds of things that you can ultimately use in both production pass-fail and laboratory audit testing and product development.